The first one's a construction. So real quick, as if you've been watching my videos throughout this entire review process, understand that I show the construction here on my computer software, then I jump to a hands-on version of the construction. So if you want to see it this way, fine. If you want to see it as if you were to actually hold a compass, that's the next section. Here we go. Number 25. Given trapezoid JKLM with JK parallel to ML, using a compass and straight edge, construct the altitude from vertex J to line ML. Well, the first thing that I need to grab is a straight edge, and I need a compass. Perfect. So what we're going to do is we're going to construct the altitude. Now, you have to remember what is the altitude again? Well, the altitude is perpendicular to its base. Whatever it is. It could be a triangle, it could be a trapezoid, it could be a parallelogram, whatever it is. And altitude is drawn perpendicular to its base. But in this case, we're drawing it from J to ML. So we need to use some basic knowledge of constructions to get this right. This is a classic example of a perpendicular line, drawing a perpendicular from a point not on the given line. The given line in this case is actually ML, so we actually need to construct a line that's perpendicular to ML from point J. Well, how do we do that? I'll show you. The first thing that you're going to do is you're going to take your compass and you're going to place the compass point on J. Or if you're using a safety compass, you place the plastic piece that swivels on point J. Now, what we're going to do is we are going to then extend our compass a little bit more, or a little past line ML, but enough that we could actually swing the compass in both directions and intersect line ML at 2 points. The 2 points of intersection are here and here. If you expand your compass too far, you're going to miss. It might make an arc over there. You got to go smaller. So now what I'm going to do is I'm going to not change my compass setting. And what I'm going to do is I'm going to swing above and below using these 2 points on our line. So I'm going to place my compass point on this left point. I'm going to swing below, and I'm going to swing above. Then I'm going to repeat the process on this blue dot. Swing below and swing above. There we go. And swing above. Now, here's the thing, folks. You don't have to swing above. You could actually just swing below and you'll get credit anyway. But I like to be accurate. I swing both above and below. Now, the last thing to do is just take your compass, your straight edge, and you are going to simply connect these 2 intersection points. So place your straight edge on that intersection point and that intersection point right over here. And you are just going to draw, you're going to draw that line. Just like so. There it is. And that, ladies and gentlemen, is a altitude drawn from vertex J to ML. Now, we're going to go through this construction again if you want to, using a hands-on construction. If not, you can just fast forward the video. Okay, this is question number 25 from the June 2017 Readings Exam. This is the construction that is hands-on if you do not like the computer software that I use. So, the question says, given trapezoid JKLM with JK being parallel to ML, using a compass and straight edge, construct the altitude from vertex J to line ML. Leave all construction marks. So remember that by definition, an altitude is perpendicular to its base. So our goal is to create a line passing through J that's perpendicular to line ML. Well, how do we do that? Well, we need to understand that in order to complete this construction, we need to place our compass point on J and measure to the length of ML. This is a classic example of a point not on the given line, and your goal is to construct a perpendicular. So I'm going to place my compass point on J, and I'm going to extend my compass a little past ML. So that is slightly past line ML. What I'm then going to do is I'm going to construct an arc. What this does for me is it gives me 2 points or 2 reference points that I could use to generate my perpendicular line. Then I go back to my compass. I then place my compass point on these 2 intersection points, and I swing my compass above and below. So let me just move this up a little bit. Okay. And then I'm going to construct below, followed by an above arc. Now, you don't have to do the above arc. You could actually just do the below arcs, and you would still get full credit. And I'm going to repeat the process on this point. I'm going to go below, and then I'm going to go above. As you can see, I have 2 intersection points. I personally like 2 intersection points because it is more precise, but you could have just drew one of these arcs. That's perfectly fine. And then you just construct or draw your line through these 2 intersection points, and it has to pass through, remember, it has to pass through point J. And that is how you construct an altitude from vertex J to line ML. All right, here's question number 26. Determine and state, in terms of pi, the area of a sector that intercepts a 40-degree arc of a circle with a radius of 4.5. First thing that I want to do, draw a picture. It's always nice to draw a picture. So here's my circle, and what it's saying here is we are drawn from the center of the circle to the outside, or something like this, like a pizza slice. And it tells us that the angle intercepts a 40-degree arc. So this arc right here is 40 degrees. So this angle is intercepting this arc. And find the area of the sector. And the radius is 4.5. So 4.5. Well, you need to know what the area of a sector formula is. There are actually 2 ways that you could do this. I use it this way, then I'll show you the other way. The area of the sector of a circle, the formula is given as n over 360 pi r squared. Okay? So the n in this case represents the central angle. N represents the central angle. And the central angle is the angle that intercepts this 40-degree arc right here. So this angle, which is a central angle because it is in the center of the circle, is 40 degrees. Okay, plug it in. So the area is equal to 40 over 360 pi times the radius, which is 4.5, and you square it. Now, what I'm going to do is I'm going to type this information into my calculator. Only the blue. I'm going to leave the pi out because it specifically says in terms of pi. So I'm going to go to my calculator. TI Inspire calculator. Pretty good. 40 over 360 times 4.5 squared. Yes, it is. Okay. And you get 2.25. Fantastic. So the area of the sector is equal to 2.25 pi. That's one answer. Now, you could even express this as a fraction. You could have said the area is equal to 9/4 pi. That's perfectly acceptable as well. Now that I'm thinking about it, I am not going to show you the other way to solve this problem. I will tell you that the other area formula, because there's 2 formulas, the other area formula is A equals 1/2 r squared theta. But if you don't know how to use that one, forget that I just said that. That formula will come useful in later Regents exams or even earlier Regents exams. You might see it pop up here and there, but those formulas could both be used interchangeably. Number 27. Oh boy, I remember this one. The diagram below shows 2 figures. Figure A has or is a right triangular prism, and figure B is an oblique triangular prism. The base of figure A has a height of 5 and a length of 8. And the height of prism A is 14. The base of figure B has a height of 8, length of 5. The height is 14. Okay, fine. Use Cavaliere's principle to explain why the volumes of these 2 triangular prisms are equal. When people took this exam, they didn't know what Cavaliere's principle was because this was the first time that the state of New York was testing it. So, this is, I'm going to talk for a little bit. I'm going to lecture to you. This is what Cavaliere's principle states. If you have 2 prisms, it doesn't matter what prism it is. It can even be a cylinder, okay? the perfect example that I'm thinking of for cylinders is a stack of quarters, okay? If you have 10 quarters side by side, and you take one of the stacks and you simply push against it, it will form an oblique cylinder. It will look something like this, right? It looks something like this. The quarters will be leaning on its side. Of course, not that dramatic, but the quarters will be leaning on its side. Does that have the same volume as the quarters next to it? They're both 10 quarters. Do they have the same volume? Do they take up the same amount of space? Yes, they do. And that's what Cavalieri stated. He basically said it doesn't matter how you orient or push the prism, it still takes up the same amount of space if the heights are equal and the base areas are equal. So I'm going to put that into words. We're going to talk about it, and we're going to finish this problem. Here we go. The first thing, the first step that you got to figure out is you need to calculate the area of both of the bases to prove that they are the exact same area. So these are both triangles. So the area formula of a triangle is 1/2 base times the height. In this case, the base is 8 and the height is 5. Okay, so the area of this triangle is equal to 1/2. The base is 8, the height is 5. The area of the triangle is equal to 1/2 times 40. 8 times 5 is 40. 1/2 of 40 is 20. So that's the area of this base of figure A. Let's figure out for figure B. So the area of the triangle is still 1/2 base times the height. It's still a triangle. In this case, the 5 is the base. The height is your 8. The area of the triangle is equal to 1/2. The base is 5. The height is 8. As you can see, it's the exact same thing over here. It's just swapped. And by the way, multiplication is commutative, so the answer does not change even if the order is switched. So the area is still 20. Okay? So now that we just proved that the base areas are equal and the heights are equal, they tell you that the heights are 14. They're the same height. We can use Cavalier's principle to prove that these figures have the exact same volume. Here we go. What you need to say is this. The volumes of these two, I don't know what that was, of these two triangular prisms are equal. Because, and this is the Cavalier's principle part, because if two solids, or just a prism, two solids have the same height, move it up here, have the same height and same cross-sectional area at every level, then the solids have the same volume. Well, what in the world does that mean, Trevor? I will tell you. I basically just put that into words what I just said before. These two triangular prisms have the exact same base area. I said that here. It says, let's see. Okay, I said it a little differently. The same cross-sectional area at every level. So basically, if you just slice these at every single level, the areas are equal. Doesn't matter how you slice it, it's still equal. And the height is the same. So we know for a fact that these two prisms are equal, or equal in volume, by Cavalier's principle. And that's how you do that question. Moving on to question number 28. Here we go. When volleyballs are purchased, they are not fully inflated. A partially inflated volleyball can be modeled by a sphere whose volume is approximately equal to 180 inches cubed. After being fully inflated, its volume is approximately 294 inches cubed. To the nearest tenth of an inch, how much does the radius increase when the volleyball is fully inflated? Okay, you need to set up two equations. I'm going to call this here Actually, first of all, you need to know the volume of a sphere. The volume formula of a sphere, which can be found on your reference sheet. I did that again. The volume of the sphere is equal to 4/3 pi r cubed. That is the volume formula of a sphere. Pretty important to know that. Now, what I'm going to do is I'm going to calculate the volume of the deflated volleyball. Okay? Well, the formula is still 4/3 pi r cubed. It doesn't matter. It's still a sphere. It's just deflated. Okay? So what I'm going to do is I'm actually going to find the radius because we're given the volume. Okay? If we're given the volume and we're given all these other constants, we need to find that radius. They want to know how much the radius increases by. So what I'm going to do is I'm going to take that 180 inches, which is the deflated volleyball. I'm going to plug it in to my formula. So 180, which is the volume, equals 4/3 pi r cubed. Your goal is to isolate this piece right here. You're trying to solve for r, not r3, but we're going to deal with that later. You need to solve for r. So the best thing to do is you need to multiply by the reciprocal of that. The reciprocal of 4/3 pi is 3/4 pi. Because the pi is really in the numerator. So you move it down to the denominator along with the 4, and you move the 3 up top. You just flip that fraction. And what you do to the one side of the equation, you must do to the other side of the equation. These cancel. Then I'm actually just going to leave this in its form. So if we take 3 times 180 and divide that by 4, you get 135, right? So this is actually 135 divided by pi. All I did, folks, is I just simplified these numbers to make it a little bit smaller for ourselves, and I just smacked on the pi at the end. Equals r to the third. Now, this was a tricky question because if your geometry teacher did not tell you how to do this in your calculator, you probably got it wrong. You need to take the cube root of both sides. The cube root is similar to the square root, except it has an index of 3. So now, once we take the cube root of both sides, we're going to get an approximation. R is approximately equal to what? So, on the TI Inspire, let me get a clear document here. On the TI Inspire, your cube root button is Control, and you see the little up arrow here on the left-hand side? It says N radical X. That's what you want, because it has a little box here. I'm going to put a 3 there, and you're going to put 135 divided by pi. Your answer is 3.5026. So I'm going to round that to 1 decimal place. Just because there's a 0 there, it doesn't really matter. Or if you want to make it 3.503, that's fine as well. Actually, let me do that. 3.503. Okay, 3.503. Now what I'm going to do is I'm going to find the volume of the inflated volleyball. Oh, sorry, the radius of the inflated volleyball. So let's go ahead and set up that equation. The volume of the inflated ball equals 4/3 pi r cubed. Here we go. The volume of the inflated ball, they tell you, is 294. That equals 4/3 pi r cubed. We're doing the same thing here, folks. We're going to multiply by the reciprocal, 3/4 pi. 3/4 pi. That cancels with that and everything else. Take my word for it, when you simplify this by the coefficients, that will give you 441 over 2. That should be a 1, not a 4. 441 over 2 pi, and that equals r to the third. Now, from here, we are going to take the cube root of both sides again. Okay? And we get r is approximately equal to the following. So take the cube root of 441 over 2 pi. Make sure that you use parentheses, folks. That is not right. The pi needs to be in the denominator. You see how this calculator sometimes tricks you? You need to be very careful. That pi is supposed to be in the denominator. Your answer is 4.125. Approximately 4.125. Now, the question is asking you, how much does the radius increase? So what you need to do is you need to take this volume here this radius over here, that 3.503, and subtract it from that radius. So I'm going to do that right now. So I'm going to take the big radius and subtract from the little one. So that's just going to be 4.12 minus 3.5. That gives you 0.622 when you plug that into your calculator. So it's asking you for the nearest tenth of an inch. 2 is not greater than 5, so the 0.6 stays. So your answer is the radius increases by 0.6 inches when inflated. And that, ladies and gentlemen, is a pretty tough part. In my opinion, that was a tough part 2 question. I did not think that was a fair question to give you on this exam.
Okay, so question 29 states, in right triangle ABC shown below, altitude CD is drawn to hypotenuse AB. Explain why triangle ABC, so I'm going to highlight triangle ABC, here's my similar symbol, is similar to triangle ACD. So I'm going to highlight ACD in yellow. Okay. So we're given altitude CD. So we know CD is an altitude. And we know that an altitude forms right angles. So since I know CD is an altitude and it forms right angles, I'm going to draw in my right angles. So here's CD, so it forms a right angle here, as well as a right angle over here. So we have 2 right triangles here, ACD and CDB. But we also know that CD is drawn to hypotenuse AB. So since AB is a hypotenuse, then angle ACB is a right angle. Because we know the angle across from the hypotenuse is always right. So the angle across from AB is right here. So that's a right angle, angle ACB. So remember, we're focusing on triangle ABC and triangle ACD. So we notice here that triangle ACD has a right angle and triangle ABC has a right angle. So we know angle ACB, we just stayed here, is equal to angle ADC, this right angle here. And I can put in parentheses right angles. Okay. So now let's also notice that angle A, so angle A here, is in triangle ACD, and it's also in triangle ABC. It's in this yellow triangle and in the pink triangle. So angle A is in triangle ACD and triangle ABC. Thus, angle A is equal to angle A, and remember this is by the reflexive property. So therefore we have an angle ACB in this big triangle is congruent to angle ADC in this yellow triangle, as well as angle A is congruent to angle A in the big pink triangle. So finally, therefore I'm going to use my 3 dots. Triangle ADC is similar to triangle ABC by angle. One of the properties that we learned. One of the similarity properties. In question 30, it says triangle ABC and triangle DEF are drawn below. So it says if AB is congruent to DE, so I'm going to draw that into my picture. So AB, I'm going to do a dash, is congruent to DE. And AC is congruent to DF. So I'm going to do 2 dashes now. These are different line segments. And then lastly, we're given that angle A is congruent to angle D. So I'm going to do an angle mark for angle A and an angle mark for angle D. So it says write a sequence of transformations that maps triangle ABC onto triangle DEF. So we're trying to get ABC to map onto DEF. So we have to line the corresponding angles, so angle A and angle D have to match up, as well as the corresponding sides. Excuse my dog. So angle AC, side AC has to match up with side FD, as well as side AB has to match up with side ED. So it says write a sequence. A sequence means more than one. So we have to state more than one transformation. So my first transformation I'm going to do is I'm going to translate. So remember, translate means to move this triangle up or down, or to the left or to the right. So I'm going to translate triangle ABC, so you have to mention which triangle you're talking about, so that C maps to F on triangle DEF. Okay, so now I'm going to sketch it out so I can see what my next sequence has to be. So I'm translating this triangle so that C lands on F. So it looks like it's going to translate up and to the right a little bit. And when I do translate it, I'm just going to sketch it out. It should look something like this. My lines are not straight at all. All right. And I'm just going to carry over what I know is corresponding to what. So I know AB has 1 dash, AC has 2 dashes, and then we know that angle A has 1 angle mark. Okay, so now what I want to do is I want angle A to align with angle D. But I also know that angle B, I'm going to do 2 dashes, is the other angle next to this 1 dash side. So here's my 1 dash side. We know angle D maps to angle A. So that means angle B and angle E have to map up to each other. Okay. So now what I want to do is I want angle A to map onto angle D and angle B to map onto angle E. So in order for me to do this, I have to turn this triangle this way, in this direction, to get A to map to D and B to map to E. And this translation, so this second, transformation. So the second transformation is called a rotation. So I'm going to rotate triangle ABC. So I have to mention the direction of the rotation. So if I'm rotating this way, that is clockwise. And then I have to say when to stop. So I'm going to rotate triangle ABC clockwise until angle A maps to D. So until A maps to D. And until B maps to E. So once we do that transformation, then we see that triangle ABC maps fully onto triangle DEF. And that is it.
All right, number 31. Line N is represented by the equation 3x plus 4y equals 20. Determine and state the equation of line P, the image of line N, after a dilation of a scale factor of 1/3 centered at the point 4, 2. Okay, first things first. I am going to put line N into mx plus b form. So your goal is to put this into y equals mx plus b form because we could work with this form. So we get 3x plus 4y equals 20. That's the line that they gave us. I'm going to subtract the 3x on both sides. We get 4y equals negative 3x plus 20. Okay? From here, I'm going to divide by the 4 on both sides. So we get y equals negative 3/4 x plus 5. Let's go ahead and graph that line. 5. Okay. So, if I were to go up to the y-intercept, that 5 is a y-intercept. 1, 2, 3, 4, 5. And your slope is down 3 to the right 4. Down 3 to the right 4. Down 3 to the right 4. And then just go in reverse. Up 3 to the left 4. And we could stop there. So what I'm going to do is I'm just going to simply create a line. All right, here we go. There's my line passing through all those points. Not too bad so far. Now it says determine and state the equation of another line that they don't give you, line P. The image of line N after a dilation with a scale factor of 1/3 centered at the point 4,2. Okay, it's centered at the point 4,2. Let's find the point 4,2, shall we? 1, 2, 3, 4, 1, 2. What is going on here? Ladies and gentlemen, the point 4,2 lies on the blue line. What does that mean? Well, it means that your dilated line is the same thing. Your answer was on the freaking paper. That's the answer. So what you have to say, and there's a reason why they say explain your answer. They're not dummies. They want to know why you know what it is. So here's your answer. Line P is actually the same line. 3x plus 4y equals 20. Well, the question is why? Here's your explanation. Since the line, I'm going to put that in parentheses, since line N contains the center of dilation the slope and the y-intercept remain unchanged. So if the center of dilation is on the line, the slope and the y-intercept remain unchanged, meaning it's the same line.